this is what you can expect on this unit. I'm hoping we can get through this a little quicker, given that we have, what, about how many weeks till spring break? Is it only 2?
Spring break till very last week of March.
I do know we lose a day next week with assembly. Is it only 2 weeks? 1, 2, no, 3. Yeah, 3 weeks. So my goal is to have this test before that time. There's no way we want to sort of put it off. And even if we did put it off, it would be like the first day back, which would be no good for anyone. So we will aim for that to be done. We got 3 weeks plus 2 days. Oh yeah, we should be.
Maybe that with the provincial exam.
That's true. But that doesn't make it a good idea. So we will solve vector problems for objects in equilibrium. Oddly enough, that's one of the last things we do. What do you think equilibrium means? Well, I'll come to that, I guess. Calculate the forces acting on an object resting on the inclined plane. That's a fancy word for a ramp, including the normal force, friction force, components of the gravitational force. We will calculate the components of F gravity exerted on an object resting on an inclined plane, so lots of ramp stuff. Solve problems with friction for objects on a horizontal surface and again on an inclined plane. Solve problems using F net equals ma, where F net is equal to F applied plus F friction, and using kinematics equations from previous units. So in fact, a lot of the kinematics that we just did will be expanded, and I'll expect you to read or be able to do it again. So there's sort of that opportunity for almost redo on some of the concepts, right? Including an applied force at an angle to horizontal motion, combined mass systems, an applied force at an inclined plane, forces acting on various angles on a body, and performing an experiment to investigate forces acting on objects. The first lab of the year will be in this unit. These are the different problem types. Horizontal force, no friction, which is really what you did in grade 11. Horizontal force with friction, which is kind of like what you did in grade 11. Angled force with friction, I think you did a little bit of that in grade 11, so we'll be sort of expanding on that. Angled surface, i.e. a ramp or inclined plane. No friction, with friction, and the movement could be up or down the ramp. And equilibrium, which means either no movement or motion at a constant speed kind of thing. This is an entire course, and in fact, it's an entire job. It's called civil engineering. It's called statics. Guys that build bridges and roads and things that are supposed to not move. Not guys, people. Statics. Okay, so there's kind of the lesson plan. That doesn't mean 1 day per each, but that's sort of the little subunits. Today is review free body diagrams, so that'll be 1 day. And then tomorrow we'll review net force problems from grade 11 and those kind of things, and then we'll get right into the inclined plane. So let's begin with those free body diagrams from last year. Now, some of you that just finished grade 11 will recognize this handout. Okay, so before we can do any dynamics, we need to have a good understanding of a free body diagram to sort of be able to identify, I guess, all the forces and be able to draw them and have an understanding of their direction of it. So we spent a little bit longer on this in grade 11. We're going to sort of zip through it reasonably quickly. So you did these questions once already. So a book is at rest on a tabletop. Diagram the force acting on a book. We draw them with boxes. What's the force down called? I call it the weight force, FW. Some people might call it FG, force of gravity. And then you'd have the F and the normal force. Remember that? Normal force. And in that case, those vectors should be equal, balanced, right? But you would say that the net force is how much? 0. Right, you are. A girl is suspended motion from the ceiling by 2 ropes. Diagram the force acting on the combination of the girl and the bar. So you can almost always start with weight force. In this case, because there's 2 ropes, many books would show it as FT tension force, but there'd be 2 of them. You could label them 1 and 2. You have to remember that the labels are really just your way of sort of communicating what they are in your mind. So you don't necessarily have to follow the same labeling all the time or the same labeling as me. That said, FW is pretty standard, right? So you could call these FT1, tension force 1. You could call it FA1, it's an applied force. I guess you could call it FAA and FAB if you want, right? So don't get too hung up on the labeling. It's just a way of describing. Negatives free falling from a nest in a tree, neglect air resistance. Diagram the forces acting on the egg as it is falling. So you should have just gravity. There is no air resistance. Just FW. Flying squirrel is gliding with no wing flaps from a tree to the ground at a constant velocity. Consider air resistance. Diagram the force acting on the squirrel. So again, you'd have the weight force, and because you are worried about air resistance here, you would have that. What would you label it? F air or FF? It's a friction force really, right? But regardless, they should be equal and balanced, right? Some people might say the flying squirrel is moving to the right, and there's some air resistance this way, so you might have to actually put something like that. It depends on the situation. A rightward force applied to a book in order to move it across the desk with a rightward acceleration. Consider friction. That neglect air resistance. Diagram the force acting on the book. So you should have weight force. I need to give myself more space here, didn't I? Weight force, there would be Fn, normal force. There is friction. It's moving to the right, so we would have a small amount of friction, FF, and then you'd have a big, giant applied force. And as I said back in grade 11, if one force is supposed to be bigger than the other, make it considerably bigger. I shouldn't need a ruler to determine if one's bigger than the other. This time it's at a constant velocity, so what's different here? Weight force down, normal force up, friction force, applied force. Those forces should be equal. The ones to the left and the right should be equal, right? Constant velocity. That is a key term to watch for. College students rest the back pocket upon his shoulder. The pack is suspended in motion by one strap from one shoulder. Diagram the vertical forces. So again, it's on Earth. Weight force. This would be a tension force because it's in a rope or a strap. Can't get rid of that. Skydiver is descending with a constant velocity. Consider air resistance. Diagram the force acting on the skydiver. Again, weight force. You'd have friction force or air resistance, whatever you want to call it, and they would be equal because he's falling at a constant velocity. Force applied to the right to drag a sled across loosely packed snow with a rightward acceleration. Loosely packed snow. There's some code words in there. Does that mean no friction or some friction? Loosely packed snow means some friction. If you've ever run through snow, you know there's considerable amount of resistant force. So rightward acceleration. So you'd have the weight force. You'd have the normal force. Here you'd have friction. It's a rightward acceleration, so FA, applied force. Yeah, makes sense? I don't know what this is over here. A football is moving upward towards its peak after having been booted by the punter. Neglect air resistance. Diagram the force acting upon the football as it rises upward toward its peak. So football is played on Earth. Weight force. Anything else? There are no other forces. Why? Because it's after it's been booted, after it's left his foot, her foot. After the football has been kicked, there are no other forces. Why is it moving? Because objects in motion stay in motion. Right? There is no force. You do not need an arrow showing the direction that it's going. You're only diagramming the forces. This is the key one in the whole segment. Right? So make sure you're aware of that. A car is coasting to the right and slowing down. Neglect air resistance. Diagram the force acting upon the car. So coasting to the right. So you'd have weight force, normal force, and it's coasting to the right. That means that your foot is off the gas. No applied force, just friction. Okay? No applied force, just friction. Is that all coming back to you now? Yeah? Yes, no, maybe so?